Okay, ladies and gentlemen, now let us move on to our next property, which is the circular frequency shift property. So, what does the frequency shift property says? It is quite similar to the frequency shift property of DTFT, only difference being that it is shifted circularly. So, if x of n has a DTFT pair of x of capital K, then as per the property, if the signal is shifted in the frequency domain circularly by a value of L, this will result e to the power j twice pi ln over n, this expression to be multiplied in the time domain. That means if you want to shift the frequency domain signal by a value of L, all we need to do is just multiply this expression e to the power j twice pi n times the amount to be shifted over capital N with the time domain signal and take its Fourier transform, we will get the shifted value of the frequency domain. So now that being said, let us move on to the proof. We know that DFT of the signal x of n is summation where n goes from 0 to n minus 1 x of n e to the power minus j twice pi kn over n. So now our signal here is x of n times some other value. So the DFT of x of n e to the power j twice pi ln over n will give us summation where n goes from 0 to n minus 1. Previously the signal value was x of n. Now the new signal is x of n times e to the power j twice pi ln over n, and consequently multiplied by this factor e to the power minus j twice pi kn over n. So we can multiply these two exponents and this will give us summation where n goes from 0 to capital N minus 1 x of n e to the power minus j twice pi k minus l n over capital N. Now once again what we are going to do is multiply both sides of the expression with the integer value 1. So multiplying both sides with 1, where 1 is equal to e to the power minus j twice pi small n times capital N over n. So this will result the left hand side being same, DFT of x of n e to the power j twice pi ln over capital N. The right hand side being summation x of n e to the power minus j twice pi k minus L n over n times e to the power minus j twice pi small n times capital N over n. Of course, the running sum goes from small n equals 0 to capital N minus 1. Now, once again multiplying these two exponents, we get summation where n goes from 0 to capital N minus 1 x of n times e to the power minus j twice pi n times n plus k minus L over n. So this is our expression. Now this can be written as the Fourier transform of x of n plus k minus L, is it not? Because the value of k has changed from k to n plus k minus L. Now this expression, as I have shown before in the previous property, is nothing but the circular shifted value where x is circular shifted by a value of k minus L for an endpoint signal. Because in the earlier property we have shown that we can write this value x of negative n as x of n minus n. So simply we can write x of k minus L as x of n plus k minus L, or we can write x of n minus k minus L. All will result in the same value. One is being denoted for advancing the signal, and if we replace this plus sign with a negative sign, it means a delay of the signal, but the value will be same. So then this is our frequency shift property. Now let us go to the circular time shift property. So the circular time shift property. So what does the time shift property state? If x of n being any discrete signal has a Fourier transform pair of capital X of k, then as per the circular time shift property, if the signal x is shifted in the time domain by any integer value L, the corresponding value in the frequency domain will be x of k e to the power minus j twice pi k L over n, which in short means that if we want to find out the shifted signal, the frequency, the Fourier transform of the shifted signal, all we need to do is just simply multiply the Fourier transform of the original signal by a term like e to the power minus j twice by k, L being the number of values by which the signal is shifted over n. So let us go to the proof. Now from the equation of IDFT, what do we get? From IDFT we can write x of n is equal to 1 over n summation where k goes from 0 to n minus 1 x of k e to the power j twice pi kn over n. So simply we can write x of n minus L to be equal to 1 over n, k goes from 0 to n minus 1. Now, since this and this value are not the same, what I mean to say is this: the expression of here and here that is shown is not the same. We can write it to be x of n plus n minus L. But then again, this value and this value is not the same. But we can change the value from n to 0. This is once again a peculiar property, and you have to take my word for it. So this is x of n minus L. So this can be written as x of k e to the power j twice pi k n minus L over n. Now summation where k goes from 0 to n minus 1, we expand this exponent to two parts. We get x of k e to the power j twice pi k L over n times e to the power j twice pi k n over n. So now, looking back and comparing it with this expression, we get this being to be equal to the IDFT of x of k e to the power minus j twice pi k L over n.